Hello everybody, this is Dr. Day with Physics 150. I wanted to give an example of solving torque problems. Before we get into this, however, I want to be clear that the problem I'm solving here is more complicated than the one we've asked you to do on the homework. However, in working through this, we're going to see a lot of the principles and pieces that we need to understand. You're welcome to fast forward through this video and find any part that works for you, any part that looks familiar. I've chosen a problem not directly from your textbook, but it's similar to one of the ones in your textbook that helps you just really understand what's happening with torques. So we say there's a helpful sign is suspended from a flagpole of length L and it's supported by a thin cable. The mass of the sign is ms and the mass of the pole is m. Find the tension if the sign is stable. And so what do we mean? We're finding the tension in this thin cable right there. That is, you've probably seen this sort of thing before. This cable is put in such a way so that this pole is held to be stable. So a couple things to look at real quick to understand before we get into this is this junction right here where the pole comes to the wall is what we call a pin geometry. If I zoom in and look at this, there's basically this pole right here is this black part, and there's a pin that kind of goes through it. So this is allowed to freely rotate up or down, but it can't move left or right. It can rotate, can't move up or down. And so what's going to happen is this pin is going to put a force on this object, which I'm going to call a normal force. But it's not going to be just this way or that way. We're going to have to allow for it to be in a different direction, maybe this way or maybe that way. We'll examine a little bit further. The point is however this pole is pulling against the pin will determine what that force is going to be. So, first thing to know is when we say stable, we mean equilibrium. And now that we're in extended free body diagrams, we have to think about two conditions. We have to think about forces. We have to think about torques. So the first thing we realize is what we've done before, and that is the sum of our forces in the x direction and the sum of the forces in the y direction must both be 0. And now we have this new symbol tau, the Greek letter for T basically. So the sum of the torques has to be 0 at all points. Now, what does that mean? Well, as we're going to see, we can calculate a torque around a different point. And any point you calculate has to sum to 0 torques. And so that's always a really confusing statement for students. They want to know, do I have to sum it everywhere? Well, you can't sum it everywhere. You sum it a few places and you make sure that it works out. But it is sort of this strange thing of, what does that mean at all these different points? Well, so let's talk about what torques are. If I think about this pole, right, and I think about this tension in this cable being applied to that pole, what's that going to do? If there was nothing else happening, right, if I didn't have gravity or anything else, and I just put that tension, you wouldn't be surprised to find that this pole now begins like turning upwards. So this tension in this is basically causing this pole to turn around this pivot point. And so torques are what cause something to turn, to begin rotating. So forces cause translation and torques cause rotation. And in many motions, you can simultaneously have translation and rotation, both occurring at the same time. Fortunately for us right now in this term, we're just worrying about the static equilibrium, meaning we need the conditions to be true so that nothing begins moving. So the first thing you begin doing in a torque problem is you draw a free body diagram just like you've always done. So here, if I look at this system and I draw my free body diagram for my pole, and actually that's not the one I should start with. I should start with the free body diagram for the sign. So this is the sign, here's its weight force, and then the only other thing making contact is tension. So there's my tension. They have to have the same length because this is an equilibrium. And that's going to be helpful for us because this little tension here will be needed later on. So now I think about the free body diagram for this pole. Now, because I can consider this pole moving or rotating or turning, I can't just draw a dot. I have to do this extended free body diagram, which means I draw the object. So now I have basically drawn my pole, and the first force I add to it is its weight. We assume it's a relatively low weight. Then the sign is the big heavy thing, right? That's the thing we're supporting. So that's creating a tension on this downward. And then there's also going to be another tension here in this line, which I've got. And then, as I mentioned before, this pin interaction is going to create some kind of force, which is going to be, in some direction. I've chosen it to be up at some angle of theta arbitrarily. When you do the math, you would find out whether that was right or not. We're going to stop just short of determining those components because we don't need those for today. But in looking for them, we're going to learn a lot of the physics that we want you to know. So, really quickly, we can see that this tension here is going to be equal to that weight, else this sign would move. And so we're just going to do a free body analysis on the flagpole. So we pick our standard XY coordinate system because that allows us to break down as few forces as possible. We sum our forces in the Y direction. Hopefully we all understand what this is. This tension here will have a Y component and an X component. So there is its Y component. Then there is a normal force from that pin, which is going to have a Y component and an X component. So there's its Y component. We subtract the weight of the pole, and we subtract the tension from the sign. That has to be, by Newton's second law, equal to ma, which has to then be equal to 0. So then we get, now we get that TCY, which is the tension of the cable Y, was that, all adds up to 0. And when you look at that, you say, okay, am I done? Did I find TC? Well, not yet, because what do we have? We've got one equation here, and we have two unknown variables. And as you know, you can't solve two unknown variables with one equation. Well, you could also have done the sum of the forces in the x direction. And that one's actually not hard. That's going to be a positive nx minus tcx. And that is then going to be equal to max, which is going to equal 0. And so then you're going to get nx basically equals to tcx. And you might say, well, am I done? Is that it? Well, the answer is no. And why is the answer no? Well, what is this TCX? This is going to be something like T cosine of theta or T sine of theta. So really what we've got is an angle that's unknown in the normal force, x, y components that are unknown. We have 3 unknowns and 2 equations. So that's not going to be enough. And it's not really surprising, right? If you think about it, we asked something about torque, and you can only solve it with normal, or forces. No, you're going to need to use the new tool. But sometimes forces will give us part of what we need, and we can work with it. So let's go back now and look at a torque analysis. So again, what is torque? Torque is basically sorry, it's late at night. Torque is what we often call a turning force. Torque is what causes an object to rotate around a particular point. The formula for torque is Rf sine of theta. What is R? R is referred to as the moment arm, or the distance from the point of rotation, or the distance from the pivot to where the force is acting. And so what you always want to do is you always want to put the vector that goes from your pivot to where the force is, and the force at the common origin, so you can determine the angle between them. So you got to remember that this theta isn't just an angle in the problem, it is always the angle between those. And then a note on conventions, we always use clockwise to be less than 0 and counterclockwise to be greater than 0. And if that is something you don't recall because you've only ever had an Apple Watch, something that goes this way is clockwise. Something that goes this way is counterclockwise. And so we have a convention based on something called the right-hand rule that determines what's plus, what's minus. Do you have to use our convention? No. But you have to use a convention that treats those two different things as plus or minus. I think it's easier to just use the one we use. And then also another note on signs that is useful. Go and take a look there if you don't remember your trig so well. So let's say now we want to calculate our torques about the center of mass. That is, we want to ask the question, how does the normal force cause this pole to rotate? How does that tension cause this pole to rotate? How does this tension cause this pole to rotate around its center of mass? Now, how would I know to do that? Well, you don't. it's often convenient to choose a center of mass, but you certainly don't have to. I'm doing that here, and we're going to see it's actually not the best way to do it, but I'm doing it here because it's a pretty natural thing to do. And so we think about this, okay, here's the center of mass. The radial arm from the center of mass to the normal is this right here. That is this r vector being drawn here. It has length L over 2 because the whole thing is length L. That force is acting up here at some angle of theta. And the torque equation asks for the angle between those two vectors. So the whole thing is pi, meaning this is pi minus theta. So then the torque that we get from this normal force about the center of mass is L over 2 times n times sine of pi minus theta. Now, why isn't it nx or ny or something like that? Well, in this formula, this is the moment arm times the whole force, not a part of the force. It's the whole force. And anything that's not properly lined up, that may be contributing a little bit less or more because at an angle, is all going to come out of this sine formula. So if I were to put in nx or ny here, I would be double counting that same effect. So this is the torque created by this normal force. And I guess I'll put a little n on it to help us remember. And then that torque is in a clockwise direction. How do you know that? Well, again, what we're saying is imagine this is the point it rotates around. Not that it really does, but we're thinking about it that way. If this normal force were allowed to change the orientation of this rod, it would cause it to rotate this way. And that's clockwise. Clockwise is negative. There you go. So now we're going to look at the effect of the tension from this string, which we know the tension from the string is equal to the weight of the sine, but we're still going to call it the tension of the string so that we don't put the weight vector on the wrong thing. And so this tension here is acting at a moment arm of this length. Well, how long is that length? Well, it's not L over 2. And sorry, there's an assumption that the center of mass of a pole is at its center, meaning that the same amount of mass that's on this half is equal to the same amount of mass as on that half. So that is, we treat the middle as being the balance point. So like if you could put the pole on your finger and balance it, it would balance at the middle, meaning half the weight was on the left and the other half the weight was on the right. So now what we've got here is we want to calculate what is the turning force, what is the torque from this tension around this center of mass. And so this again is our moment arm, which again is not L over 2. We see there's this weird little cryptic A up here. This A is L over 10. So that is, the sine isn't at the end of it, it's L over 10 offset inward. And so that moment arm is going to be L over 2, which is the whole thing, take away that amount A. So the torque is then L over 2 minus A times the tension of the string times sine of the angle between them, which you can see is 90 degrees here. So now just doing a little bit of algebra, we're able to reduce that to 2/5. We know the tension's equivalent to the weight. We plug that in, and here is now our tension from our sine. And we see that about the center of mass, this tension would cause a clockwise rotation in the same way that this normal would cause a clockwise rotation. So both of these torques have the same sign. They're both going to be negative. Now they're not negative here. They're going to be negative when we use them. So now we have our final torque to consider, and that is we have TC. So TC, or the tension in our cable, it's acting up at that angle, which is, because this is 60 degrees, that's 30 degrees. That's what this comes from. And so the angle between these guys is going to be basically pi minus 30, or sorry, 180 minus 30, or, whatever, right? In terms of radians, pi minus pi sixth. And so the length of this moment arm to where this acts is L over 2. The force is TC. Sine of the angle between them is sine of 150, which is going to give us a half. And when you plug that in, you're going to get L over 4 TC, and that's counterclockwise. Why? Because around this point, this would cause rotation this way, opposite of the clock direction. And so that torque is going to be positive at the end of the day. So now when I go and I sum my torques, why don't I have a torque for this weight? Well, there's two reasons. The first one is torque is RF sine of theta, right? And how far is this acting from the point of our pivot? Well, the answer is 0. Our pivot is right here. So this force is 0 distance away. So RF sine of theta, R is 0, torque is 0. The other way to think about it is if you have a pencil and you just balance it on your finger, if you push up or down, you're not going to cause rotation. Now, it might fall, it might slip, but it's not going to rotate because you're pushing it up or down. And so putting a force through the center of mass of an object won't cause it to rotate about that center if nothing else is being applied to it. So we're now going to sum these torques around the center of mass. We just calculated torque 1, torque 2, torque 3. And so we're going to get our first torque, which is positive here, L over 4TC. We're going to get our next torque right here, which has got a negative sign. And we're going to get our third torque. Apologize there, my screen just froze. I think we're back. We're going to get our third torque right here from there. And all of these torques have to sum up like a Newton's second law to I alpha, where I is that moment of inertia, the thing you were working with in the prior problem this week about how quickly objects rotated as they came down a hill. And then alpha, instead of being translational acceleration, it's rotational acceleration. And so when you look at this, you say, oh, maybe I solved my problem. Well, I have three unknowns here again. I have theta, I have TC, and I have normal. So I could now go back and take my three equations, 1, 2, 3, and I could solve for my tension. I'm suspecting that you can see that that's not going to be a trivial amount of work. It works, but we're going to do it a different way. And this is what we're hoping that you're learning from the problem that we're doing for Wednesday, Thursday. So what we're going to do now is we're going to choose a different pivot point. Well, the center of mass is, what did the center of mass do? If you think about it, what do we know? We know the weight of that pole. We know the weight of the sign, therefore the tension. So we know this force and we know this force. But we don't know this one and we don't know that one. But because we did our sum of torques around the center of mass, we eliminated one of the things that we knew. That's not a problem necessarily. But we included two forces that we didn't know. And that's what made it hard. So now let's think about this for a minute. Pause the video. Ask yourself, where should I sum this? And I want you to write it down. Why do I want you to write it down? We are capable as human beings of immense self-deception. Meaning you go, oh, I think it's A, and then I show you it's B, and you're like, oh yeah, I really thought it was B. So write it down. Where do you think you should sum those torques? If I summed it here, am I going to eliminate any forces? No. If I sum it here, I eliminate one of the things I know. If I sum my torques here, I eliminate another thing that I know. What am I looking for? This thing. So if I sum my torque here, I'm getting rid of the thing that I'm trying to find. I mean, it would still work in the end. You just have to do a lot more work. Instead, what am I going to do? I'm going to sum my torque here. Because doing that gets rid of this weird normal force that I don't know anything about. And it says, oh, find the torque balance between these three forces. Two of which I know. So let's do it. So we're going to choose a different pivot point. So which is that point now? We're going to choose this spot right here. So we have a torque created by the weight of the pole, which is a distance of L over 2 away from our new pivot with an mg force. So the torque is L over 2, mg sine 90. If this object were allowed to rotate, it would create a clockwise torque. So that's clockwise torque. We know that's going to be negative. We then have the sine creating a torque at that distance away, which is how far? The whole thing is L. A is L over 10. So that means this is 9/10 L. We have the tension right here, which we already know is the mass of the sign. And then the angle between those is 90 degrees. This would also cause a clockwise rotation, so that'll be a negative torque. Then we have the tension in that cable operating at a full distance of L away with a force of TC. And now that angle is a little bit harder. We've got an angle here that allows us to determine what this angle is. It's 150. And so we get LTC sine 150, which turns out to be 1/2 LTC. And if possible, if this thing actually caused rotation, it would cause rotation this way, which is counterclockwise. So we're going to have 2 negative torques and 1 positive torque. So now when I sum the torques around my pin, around where that normal is happening, what do I get? Well, now I'm just putting in my torques, the 3 ones that I calculated. Also, by Newton's second law, is I alpha equals 0. A little bit of algebra later, I'm able to find the following answer. And here's something we see that's really interesting. You might suspect that this tension simply has to equal the sum of those 2 forces to balance it out. But you see it's not. Yes, it equals the weight of the flagpole, but it's also 9/5 the weight of the sign. Think about that. What's 9/5? 1.8 or something. And that's a bigger quantity, right? And so it's not just supporting the weight, it's supporting the turning, the torque. And so that means this normal force is actually going to do something a little bit different than when maybe we thought. And if you want to try to solve that and let me know, I'd be happy to talk you through it. I want to just give you this as some assistance for today. I hope you enjoyed the video. Please let me know if you have any further questions. Thank you.